Hi everyone. Today we have the AFOMP school webinar on basic and latest technology of CT with an eminent moderator, Professor Kitiwat Khamwan from Thailand, and most eminent speakers, Professor Tsujioka, Professor Matsubara, and Professor Teramoto. And Professor Kitiwat is Associate Professor of Medical Physics in the Division of Nuclear Medicine, Department of Radiology, Faculty of Medicine, Chulalongkorn University, Bangkok, Thailand. And he is a very active member of medical physics organizational activities across the globe. AFOMP is one among them, IOMP, CFOM, and other medical physics organizations in his country. And he has many awards and honors to his credit. I am not going to read out all of them. And he is a pioneer in research activities also, with very significant contribution to the nuclear medicine research activities and in radiology. And he has a good number of publications to his credit, more than 23 publications in index journals and numerous publications in presentations in the conferences across the world. So today we have this webinar on latest technology in CT, along with the basics of it. And I would like to request Professor Kitiwat to take over and proceed with the AFOMP school webinar today. Over to you, Professor Kitiwat.
Okay, thank you so much, Dr. Mary Jones, for your kind introduction. And again, so welcome every participant to join the AFOMP webinar for the episode 10. So today we have three invited speakers that will give such a great topic regarding the latest and the basic technology of the CT. That including the basic of the latest technology in the CT that will provide by Professor Katsumi Tsujioka. And the second topic will be the basic and recent advance in CT dosimetry will be given by Professor Kosuke Matsubara. And the last fundamental of the deep learning and its application in medical Atsushi Teramoto. And again, so I would like to thank the AFOMP for inviting me as the moderator for this session and also for the invited speaker. So let's start for the first speaker first, for the Professor Katsumi Tsujioka. And let me introduce about for his background. Katsumi Tsujioka, he got a bachelor degree of radiological technology from School of Radiological Technology, Nagoya University in Japan. And he also got bachelor degree in engineering at the IG Institute of Technology in Japan. And also the expiration of graduate school IG Institute of Technology in Japan as well. So he teaching in X-ray engineering, X-ray CT engineering, ultrasound engineering, and electric engineering. He got several awards, such as the Best Paper of the Year by Japanese Society of Radiological Technology, the Best Teacher of the Year from Fujita Health University in 2016, the Future Technology Heritage of the National Museum of Nature and Science in Japan in 2018. Right now, he's on the development of the performance technology of the X-ray CT, development of automatic exposure control, and development of measurement method, temporal resolution, and also the many approach regarding the technology in CT. So right now, he serves as the invited professor at the Faculty of Radiological Technology, School of Medical Science, Wichita Health University, invited professor, Graduate School of Medical Science, Wichita Health University, and visiting researcher at the Department of Diagnostic Radiology, National Academy. So please welcome Professor Katsumi Tsujioka. So if you're ready, you can start your presentation now.
Thank you very much for a good introduction. And this time is a very happy to talk in this webinar. Now I start my lecture. Hello, everyone. My name is Tsujioka, Fujita Health University. It's a great pleasure for me to talk in this time. This is Fujita Health University. It's near Nagoya City in Japan. This time, talk about the basic and the latest of CTs. Number one is the history of X-ray CT. It's my history. I am a radiological technologist and I am an engineer of X-ray and CT machine. This is the history of X-ray CTs. X-ray CT was developed by Dr. Hansfield in the world first CT is EMI scanner, 1973. And in 1975, 2 years later, Japanese first CT was developed by Fujita Health University and Hitachi Company. And 1987, helical scan was developed in Fujita Health University and Toshiba Medical Systems. And 1994, auto exposure control in CT, CT-AEC was developed in Fujita Health University and Toshiba Medical Systems. My history of CT development is that I developed many kind of the CT hardware and software. At first, I talk about keyword. In CT machine is a single slice CT and multi-slice CT and area detector CT. And the scanning technique is a non-helical scan and helical scan. Machine name and scanning technique name is different. History of X-ray CTs. X-ray CT was developed by Dr. Hansfield. This is the first examination unit of X-ray CT by Dr. Hansfield. First X-ray CT, it is a EMI scanner. X-ray CT was developed by Dr. Hansfield. However, you know their name. They are the Beatles. The X-ray CT was developed by the Beatles. It's a very strange story. The Beatles get so many money, and the EMI company gets the money, and Hansfield worked in the EMI laboratory, and he developed the EMI scanner. So X-ray CT was developed by the Beatles. However, the original idea of X-ray CT is developed by one Japanese radiologist. His name is Dr. Shinji Takahashi. Takahashi tomography is a cross-section tomography using analog film. This is an idea node of Takahashi tomography. Dr. Takahashi developed the rotating tomography at 1946, very long time ago. His original idea is X-ray CT. However, there is no computer at 1946. So he developed the rotating tomography. Number two, basic of CT basic. This is my presentation at RSNA in 2004. The title is Helping Students Understand the Basic Idea of CT. This is a presentation that reproduced that Professor Takahashi's experiment proposed. This examination is to understand the X-ray CT machine by using conventional X-ray systems. It's the same as Dr. Takahashi. The CCT principle is data collection and image reconstruction. This times data collection and image reconstruction by using not a CT machine, it's an analog film and just a computer. The data collection method is just the same as a CT machine by using analog system. For the examination, phantom was needed, and we made acrylic an object, triangle and circle and rectangle in AGA. It's simulate as a brain. Examination using conventional X-ray unit. It's a figure, is a very simple examination. We could not see the acrylic object in developed film. It was a wrong phantom. What is a mistake? The analog system did not have so good contrast resolution like CT. So we developed a new phantom. This is our new phantom. It's a very simple acrylic object and air, no AGA, very high contrast object. Examination again. This is a result. This is one projection by using an analog film. And next is the 10 degrees rotate data. And next 10 degrees rotate data. So we take one rotation, 360 degrees, 10 degrees interval, so 36 times exposure, one rotation. Just a 180 degrees, a half rotation. "36 times projection." This is sinogram. Sinogram is the channel of detector and projection angle. Sinogram is the raw data before the reconstruction. It's the origin data. Next, we have to do image reconstruction. The Dr. Takahashi done a very hard work on the table and the paper and write data. But I use PowerPoint, one projection data, and by using a PowerPoint expand, this is one projection. Next 10 degrees rotate, same expanded data. 10 degrees, 10 degrees, rotate. This is a simple back projection. So in the center image of center of the image appears reconstructed images. I will show the result. This is a project phantom, circle and triangle and rectangle acrylic object is inside of the acrylic syringe. Top view is here. Circle and triangle and rectangle object. This is the result. Right side is a commercial CT machine, TCT60A by Toshiba. It have 800 views. The left side is the result of our analog CT examination. 36 views. Sorry, this is 18 views. Because opposed data is almost same, and this projection is only 18 views. but the result is almost same. Reconstruction was very good. So this is Dr. Takahashi's examination. The CT machine is very simple to scanning and reconstruction. Number 3 is the development of helical scan. The scanning technique is a non-helical scan and helical scan. The conventional CT non-helical scan, before the development of helical scan, we had to scan each slice at each position, scan and move and scan and move. However, by using a helical scan, we can scan whole body with only one rotating scan, continuous rotating scan. It is a volume scan. This is the advantage of helical scan. Number 1 is a good image continuity. It's a volume data collection. It's a good for 3D CT and MPR CT, and isotropic resolution is important. I talk about the isotropic resolution later. Second is a short time scan. Is a one breath hold scan, improve the temporal resolution and improve the contrast enhance effect. It's a reduction of injected contrast volume and includes the contrast enhance effect. So this is a history of developing helical scan. We use the TCT 900S Toshiba in 1987 June. It have a continuous rotating, very special machine and nutate rotate systems. So this is the first idea note of helical scan. It's October 1987. The first name of the helical scan is a very strange table sliding dynamic scan. Very simple name, but it changed to helical scan. I wrote this memo note at the family restaurant in Toyota City near my home. After that, our first examination of helical scan. The first helical scan examination is 1987. In lunchtime, I put the lung module phantom to pulling and continuous rotating. It's a very simple examination, but the result is very wonderful data. After that, I made a patient table movement. So I use a power injector for the contrast enhance. And after that, we already carried out a multi-phase CT angiogram with helical scan. It's 1987. This is a patient moving system. It's a handmade, contrast enhanced, powered, and the table movement. So it was registered as a future technology heritage of the National Museum of Nature and Science in Japan. It's a very honor. So I introduce a generation classification of X-ray CT. This is a conventional generation classification. The pencil beam and the translated rotate is Hans field first generation. So narrow fan beam need a very narrow fan beam, translate and rotate. It's a second generation. Now the commercial CT machine is a wide fan beam. It's only a rotate system. It's a conventional generation classification in textbook. So I introduced a new generation classification. All the last generation classification is only a fan beam. non-helical scan and single slice helical scan. All the last generation classification is only a thin cone beam in z-axis. So next generation in z-axis is a narrow cone beam, multi-slice helical scan. However, fan beam and narrow cone beam need to scan and translate. It's just a step and shoot and helical scan. So the broad cone beam, wide cone beam CT machine was developed. The only one rotation, we can get the three-dimensional volume data. Now the coverage of the maximum coverage is 16 centimeter for the brain and face and cardiac and liver. This is one story. 1 month after the helical scan development, I submitted such a CT idea in 1987, December. It's a 3-tube and 3-detector CT. I think it's a good idea and a good design for the CT machine, latest CT machine. Sorry, this CT is not yet. Very expensive and very difficult to make. Not yet. So go to next. Number 4, X-ray effect and CT. This knowledge is important not only CT but for all X-ray equipment. Very important for radiological technologists and medical physicists. It's only 6 X-ray effect. Number 1 is a heel effect. Number 2 is a blooming effect. Number 3 is a slant focus effect. Number 4 is a beam hardening effect. Number 5 is a scatter X-ray. Number 6 is a gradle effect and the air gap effect. X-ray effect is only 6. At first, I talk about the helical heel effect. The heel effect is depend on the target angle. Electron beam from a cathode, a filament, to anode and target. And X-rays appears from not a surface, small inside of the target. X-ray is from inside of the target. So the cathode size inside of the distance A is very small. However, anode side distance B is bigger than A. So in single slice CTs, before the multi-slice CT developed, the X-ray beam was fan shape and fan beam. It is no problem against the phenomenon of heel effect. Only use just the center of the X-ray beam. However, in multi-slice CT, the X-ray beam was conical shape, cone beam. The phenomenon of heel effect appear. The cathode side is the X-ray strength, X-ray power is high, and X-ray energy is low. And the anode side, X-ray power, X-ray strength is low, and X-ray energy is high. Different X-ray power and X-ray energy. So this is a dose profile of area detector, 320 area detector CT on the axis, and anode is smaller, and cathode is high. And the noise is different in anode and cathode. Against this phenomenon, this is my idea. By using a 3D bow-tie filter, the strength and X-ray energy will be same in anode and cathode side. This is a 3D bow-tie filter. This is my idea. but not yet in commercial. Summarize of helical Hill effect. Challenge parameter is anode to cathode side and target angle. Phenomenon is the X-ray strength and X-ray energy change at the anode and cathode side. In a conventional general X-ray, film density change at the anode and cathode side. In single slice CTs, no change because the X-ray is a fan beam, very narrow cone beam, and the multi-slice CT is an image noise at the contrast resolution change at the anode and cathode side body axis. However, CT value is no change, no problem, because each slice was calibrated. So technology in multi-slice CT is a 3D bow tie filter, but not yet in commercial. Next, focus size change effect is two effects. Number one is a blooming effect. Number two is a slant target effect. Blooming effect is a focus size change by KBP and MA. KBP increase and the focus size smaller, and MA increase and the focus size larger.
Okay, yeah, got money.
It's a very famous effect in X-ray too. So blooming effect change parameter is a KBP and MA. The phenomenon is a change of the focus size, and the result is the conventional X-ray. A general X-ray is a change of sharpness, and single slice CT and multi-slice CT is a change of the spatial resolution. The technology in multi-slice CT is the electrical focus control, the latest technique. Next focus change effect is a slant focus effect. The focus size change by anode and cathode side. The anode side is focus size smaller, and cathode side focus size is larger. This name is not the textbook. I tentatively named it. This is a slant focus effect. It's a very simple and very easy to understand. From anode side, the focus is small. From a cathode side, focus is larger. So we have to measure the center of the focus X-ray beam. The summarize of the slant focus effect, focus size change by the anode and cathode side. Change parameter is the anode to cathode side and the target angle. It's the same as the Hill effect. However, phenomenon is a different focus size change and at the anode and cathode side. In conventional X-ray, change of the sharpness and the single slice CTs, no change because the X-ray is a fan beam. It's the same as a Hill effect. In multi-slice CTs, change of the slice sensitivity profile, slice thickness in Z-axis is changed. There is no technology. Only by the fan is only a target angle change. Next is the beam hardening effect. Beam hardening is change of the X-ray energy. The element is 3. KBP and filter and object attenuation. In X-ray CTs, the small object is a very high CT number. Without BHC, calibrate size is normal. However, the object is smaller and the CT value is higher. However, by using a beam hardening correction, that's a software, the all size of the object is the same CT number. So summarize of the beam hardening effect, Change parameter is a KBP and bow-tie filter in CT and object attenuation. The phenomenon is the change of the X-ray energy and change the CT number. And the conventional CT is a change of the film contrast. Lower KB is a high contrast and higher KB is a low KB, low contrast. In CT, single slash CT is a change of the contrast resolution, shading artifact. Multi-slice is the same. The technology in multi-slice CT is a bow-tie filter and beam hardening correction, hardware and software. Next is the scatter X-ray. What parameter depend on the content of the scatter X-ray? Parameter of content of scatter X-ray is 3. Tube voltage and thickness and X-ray field size. When you change the scan time and MA, the contents of scatter X-ray do not change. Only a volume is change and the contents percentage are no change. The parameter of contents percent of the scatter X-ray is tube voltage and thickness and object thickness and X-ray field size. Scatter X-ray is how much the contents of the X-ray scatter in the conventional general radiography, general X-ray. The abdomen X-ray photography, tube voltage is 100 kbp and the thickness is patient thickness is 20 centimeter and X-ray field size is 30 by 30 square centimeter. It's a normal X-ray for abdomen. This figure in textbook, sorry, in Japanese. The tube voltage is 100 kbp and the field size is 30 by 30 square centimeter and patient size is 20 centimeter and the result scatter content is 85%. Very almost X-ray content is scatter. Primary X-ray is only 15%. By using X-ray grid, reduce X-ray scatter to about 60%. So in X-ray CT, how much scatter X-ray included in CT? Just the same as the situation of a CT machine. 64 multi-slice CT, the coverage is 32 millimeter, and 320 ABCT is coverage is 160 millimeter wide coverage. Result of the scatter measurement. The object size is 5 centimeter and 10 and 15 and 20 centimeter thickness. By using 64 multi-slice CT, coverage is 32 millimeter is almost 40%, and 320 coverage is 16 centimeter is almost 60%. Smaller than conventional X-ray, general X-ray. It depends on the air gap effect. So single-slice CT is a single-slice CT had a good contrast resolution, but the patient dose was high because the scatter is lower. So MDCT and ABCT have not so good contrast resolution, but the patient dose was low because X-ray area is wider. We must reduce the X-ray scatter at ABCT and MDCT and ABCT. And we must keep the low patient dose. It's an iterative reconstruction and deep learning reconstruction to reduce the image noise. Summarize the scatter X-ray. Change parameter is the KBP and the X-ray field size and the patient size, thickness. And the phenomenon is a change of the X-ray scatter contents and Conventional X-ray is a change of the film contrast, and single slice CT and multi-slice CT is a change of the contrast resolution. Technology in multi-slice CT is a software and 2D grid, two-dimensional grid. Reduce the scatter X-ray. Finally, it's a graded effect, air gap effect. It's a distance from object to detector. The relation of X-ray scatter is decreased when the distance of the object and the detector increases. This is an important phenomenon in conventional X-ray. However, the distance of object and detector in CT is a very long distance. This is no problem in CT. So graded effect, air gap effect in CT and CM X-ray system is no problem. It's a reduced scatter X-ray. A summarize of the graded effect, air gap effect. Change parameter is the distance of the object and detector, and the phenomenon is the change of the X-ray scatter. In CT machine is no problem. So X-ray effects, I introduced only 6: heat effect, blooming effect, slant focus effect, beam hardening effect, scatter X-ray, and graded effect, air gap effect. They are very important in all X-ray modality. So next, number 5 is the performance of X-ray CT. So CT performance is a spatial resolution and contrast resolution and temporal resolution. These are the same for the other modalities. Number 1, spatial resolution is how small object can be displayed separately. It's not how small object can be displayed. The separate is very important, and MTF is used to evaluate the spatial resolution. The element related to spatial resolution is many introduce focus size and enlargement on the number of the view and the offset detector or flying focus spot and the number of matrix pixel size and the reconstruction kernel, reconstruction filter, and slice thickness. Or in clinical situation, the radiographer and the radiotechnologists can control the reconstruction kernel and the slice thickness. So CT measures the spatial resolution of the XY plane and the axis separately. Then, what is the state where the spatial resolution of the XY plane and the Z-axis is equal? Even the resolution is the isotropic resolution. It's very important. Isotropic resolution is an important performance for the 3D CT image and MPR images. If the spatial resolution of Z-axis is inferior to XY, it is no longer isotropic resolution. Left one is isotropic resolution is very good for diagnosis in 3D. However, slice thickness is wider than XY plane. The flat noodle phenomenon appear. It's not good for 3-dimensional diagnosis. Number 2 is a contrast resolution. Contrast resolution is how small a CT volume difference can be displayed and how small the image noise is displayed. Contrast resolution is evaluated by the standard deviation of CT number or NPS. NPS is a noise power spectrum. Other name is a Wiener spectrum. Contrast resolution is elements related to contrast resolution is MA and second and kilovolt and the reconstruction kernel, reconstruction filter. If exposure dose is increased, image noise will be reduced. The very good contrast resolution. However, contrast resolution is very good. Image noise is small. However, the patient dose increase. It's a problem. the balance of the patient dose and image noise is important in clinical. So final, the number 3 is temporal resolution. How short scan is done and how short interval time scan is done. The element related to temporal resolution is the rotation time and scan system and half scan and multi-slice scan and area detector scan and helical scan. This is summarized modality in diagnostic radiology. General X-ray and X-ray angio and CT and MRI and nuclear medicine and ultrasound. The imaging principle is different. However, X-ray CT is almost good, short exam time and emergency radiology and 3D diagnosis and spatial resolution and contrast resolution. Next is number 6, real-time CT. Conventional CTs, the reconstruction is done after the scan. It is not possible to see the scan image during CT scan. So the real-time CT is we can see the CT image during the CT scanning. It is the same as the X-ray TB. This is a method to real-time CT. We use the continuous rotating CT and reconstruction is back projection for high-speed calculation. Number 1, reconstruction. And next, a part of the data is disposed and a part of the data aided. And next image. Next image. Next image. It's just a cinema images. So now, Canon Medical Systems CT machine is 12 frames per second. It's just like a movie. So real-time CT are used for 3 clinical. IVR CT, CT fluoroscope, and real-time determination of the trigger for the contrast agent injection, and real-time determination of helical scan range. At first, I talk about the IVR CT and CT fluoroscope. This is the CT NAB, needle aspiration biopsy or the lung cancer. By using a multi-slice CT NAB needle aspiration biopsy, CT fluoroscope, it's a very safety and very short time examination to pick up the tumor. Center is a center slice and the outside is DAS1 and DAS4. Very easy to pick up the tumors. Next is a real-time determination of the trigger for the contrast agent injection. Now, latest CT technique is almost a CT enhancement. The trigger CT level is set and scan start, and we can set the delay time. It's a bolus tracking. Bolus tracking using a real-time scanning allows the examination to be performed at the optimal contrast timing, regardless of the patient blood flow speed. Every time, very good contrast enhanced timing we can get. So finally, the real-time determination of helical scan range. In helical CT examination, before the CT scanning, we take a scanography and scout view and topogram before the examination. However, in CT scanning, the patient is a different breath in or breath out, it is difficult to know the rank base during CT examination. Real-time CT allows the determining the optimal timing to end of the scan. It's a very safe examination. This is our laboratory staff and student. Finally, I took dual energy CT and photon counting CT. Dual energy CT and spectral CT. There's a many company and many technology, dual source technique and fast KB switching and dual layer detectors. Dual energy CT and spectral CT is a performance is a discrimination image of a substance, iodine and calcium and fat, and virtual monochromatic image. It's a 40 kilo electron volt to 120 kilo electron volt, and the virtual non-contrast image creates a non-contrast enhanced image from the contrast enhanced images. No use CE images. So beam hardening free by monochromatic image. And EID CT, conventional CT versus photon counting CT. The clinical advantage of PCCT is ultra high resolution and energy discrimination and low image noise. However, there is some problem in PCCT, crosstalk, signal interruption, and pile-up, signal overlap, and data transmission speed, and energy discrimination. This is a crosstalk, and the left side is EID CT, conventional CT. The signals are obtained by the light to the scintillator, and the spatial resolution is determined by separators spacing. Low crosstalk due to a separator in detector. However, the separator is a problem. Right one is PCCT, photon counting CT. The ionized signal reach the anode pixel directly. The anode pixel is a very small. Spatial resolution is determined by the anode pixel spacing. No separator. However, the high crosstalk due to a lack of the separator in detector. Next is a pile-up. The conventional EID CT cannot discriminate multiple energies at the same time. However, the technology of dual energies can enable various material discrimination. So by using a PCCT can discriminate multiple energies at the same time. However, if the multiple photon energies hit the detector at the same time, the signal value will be higher due to a pile-up, 2 signal to 1 signal. Next problem is data transmission speed. For example, it's by the Siemens. Conventional CT is 0.6 square millimeter by 1 signal output. However, PCCT is a pixel size of 0.2 pixel anode size. Anode pixel size is 0.2 square meter by 4 beam. Energy separation is 4, and 2 projection is a dual source. The result is 942. The total is 72 times. PCCT require data transfer rate 72 times faster than conventional CT. It's a very big problem in hardware. EID-CT versus photon counting CT is a discrimination, energy discrimination. Currently, iodine is the only contrast agent available for energy separation. This is also possible with energy separation in dual energy CT in using EID-CT. PCCT will become effective if new contrast agents for energy separation are developed. We are waiting, and PCCT still has many technical problems. However, in the near future, they may be resolved. At that time, CT technology will be changed greatly. We are preparing for the era of PCCT. There are improved spatial resolution, new image reconstruction by artificial intelligence, AI. So this is the final slide. Thank you very much. Basic and the latest of CT. Thank you very much. And this is my friend and my students. ありがとうございました。
All right. Thank you so much, Professor Katsumi Tsujioka, for your nice presentation regarding the basic and the latest technology in the CT. And well, so in order to keep the time, and then we also have the Q&A session after ending all of the speaker. So for those who have any question, you can leave your question in the Q&A chat box, and then each speaker will answer your question. Thank you so much, Professor Katsumi Tsujioka.
Thank you very much.
So, thank you. Okay, and then let's move to the next speaker. The next speaker will be Professor Dr. Kosuke Matsubara. Okay, before we start his talk, let me introduce a bit about the background of Professor Kosuke Matsubara. Professor Dr. Kosuke Matsubara, he got a bachelor degree, master degree, and doctoral degree in health science from Kanazawa University, Japan. Right now, he serves as the full professor at Department of Quantum Medical Technology, Faculty of Health Science, Kanazawa University. He served as the various professional societies, such as the Executive Director of the Japanese Society of Radiological Technology, the Chair of Radiation Protection Division of the JSRT, Executive Director of the JSRT. Right now, his research focuses on the patient dose evaluation in diagnostic radiology by measurement and the Monte Carlo simulation, the island dosimetry, and evaluation of the risk in radiation cataracts in interventional radiology and cardiology, development of the radioprotective tool for occupational dose. And he also got the several awards, such as the he just got the Professor Pradap Athakon Memorial Lecture Award from Thai Medical Physics Society this year, Young Researcher Award from JSRT in 2019, and Radiation Protection Researcher Award in 2015. Okay, please welcome Professor Dr. Kosuke Matsubara.
Thank you very much, Dr. Kitiwat, for your kind introduction. And good morning, good afternoon, and good evening, participants. My name is Kosuke Matsubara, Kanazawa University, Japan. And it is my great honor to have a lecture about basics and recent advances in CT dosimetry in AFOMP school webinar episode 10. So can you hear me okay?
Yes, we hear you.
Okay, thank you very much. So I will start my presentation today. CT technology has made remarkable progress, and in recent years, advanced technologies such as AI-based image reconstruction And photon counting CT has begun to be used, as Professor Tsujioka explained earlier. And these graphs show relative contributions by modality category from 2009 to 2018. And as you can see, the left graph shows the annual number of examinations, and conventional radiographs account for 62.6% of annual number of examinations, and CT accounts for only 9.6%. But CT accounts for 61.6% of annual corrective effective dose, and conventional radiography accounts for 23%. So you mean CT dose assessment remains as important as ever. So today, to deepen your understanding of CT dosimetry, I will talk about basics and recent advances in CT dosimetry for about 45 minutes. So I will start from basics in CT dosimetry. So at first, I will explain about the definition of CTDI. That means computed tomography dose index. And computed tomography dose index is commonly used radiation exposure index in CT. And the CTDI is calculated by integrating over the dose profile for single axial rotation, then dividing by the nominal beam width, NT. This is the equation to calculate the CTDI. And N is the number of slices acquired per single axial rotation, and T is the width of a single acquired slice. Then NT is the nominal beam width. And because the area of this rectangle is integrated dose, this is equal with this one. So the height of this rectangle represents CTDI. And this measurement is most often made using a 100 millimeter pencil chamber, and it is called CTDI 100. And although it is very convenient method, CTDI 100 is very convenient to measure, but it always underestimates CTDI, as you can see, because it cannot measure those in the outskirt region, outside the chamber, as you can see. And this is how to measure CTDI. And when measuring CTDI, CTDI phantom, which is made of PMMA, there are two sizes, 32 centimeter diameter and 16 centimeter diameter. And larger one is used for represent patient body, smaller one represents for patient head. And it is placed, each of them is placed at the center of the CT gantry, as you can see. And an ion chamber is inserted into one of the holes. There are many holes, at least 5 holes in the phantom, and you can insert the phantom into one of the holes. And it is also important to fill other 4 holes or other holes with PMMA plugs. And air karma CTDI 100 measurements are done in all 5 holes one by one. And weighted CTDI, it is also called CTDI-W, is calculated by this equation. And in this equation, CTDI-C is CTDI 100 in the central hole. CTDI-P is average CTDI 100 in the 4 peripheral holes. And after that, the volume CTDI ball is calculated because radiation dose in radiation dose in CT scan is affected by overlapping adjacent scans or pitch factor. It is not normal to scan at the pitch factor of 1.0, or normally the pitch factor is more than 1 or less than 1. So pitch factor, the effect of pitch factor needs to be taken into account when calculating the CTDI. So CTDI ball is calculated for that purpose. And next, DLP, dose length product, is calculated by multiplying CTD eyeball by scan length. And it is important to remember that the CTD eyeball and DLP are displayed on CT console and stored in either the DICOM image header or the DICOM structured dose report. And this is dose management data flow in my university hospital, Kanazawa University Hospital. And CTD eyeball and DLP are stored in the DICOM image header, and they are transferred to the dose management server, ReadyMetrics, via PACS. And we can always see the CTD eyeball and DLP for each patient, and the ReadyMetrics also provides organ doses and effective dose for each patient. But CTD eyeball does not represent patient dose because it is a dose value based on dedicated PMMA phantoms, only for the phantoms of 32 centimeter or 16 centimeter diameter. So if the patient dose can be estimated from CTD eyeball, it would be very helpful for patient dose management. So, but for this purpose, the size correction is needed from CTD eyeball. So SSDE, size-specific dose estimate, was proposed in AAPM report number 204, and it can be calculated by multiplying CTD eyeball by SSDE conversion factor, as you can see in this equation. And it is defined as a patient dose estimate, which takes into consideration corrections based on the size of the patient. And in all cases, you can remember that the SSDE should correspond to tissue doses, not air karma like CTDI. So I will show you how the SSDE conversion factor is obtained. And first approach is using AP, anterior-posterior direction, and lateral diameters of the patient. And AP plus RAT is used for this purpose. And AP and RAT can be measured by using localizer radiographs or like this, or axial images like this. And if the localizer radiographs are used, SSDE can be estimated prior to the acquisition. And then the SSDE conversion factor is obtained from the table or regression equation provided in the AAPM report. Such kind of table is shown in the AAPM report number 204 or number 220. So by referencing these tables, we can estimate the SSDE conversion factor from AP plus RAT. These are the AP plus RAT. And if the AP plus RAT equals 18 centimeter, that means the conversion factor is 2.69 or something like this. And the second approach is using effective diameter. And the effective diameter can be calculated from the area using this equation. So this is the example of obtaining the area by using the ImageJ software. It is a free software. And by using this equation, you can easily estimate the effective diameter. And then the SSD conversion factor is obtained from the table or regression equation provided in the AAPM report. Here, effective diameter is the diameter of a circle with the same cross-sectional area, but it only has geometric information, does not have X-ray attenuation information. But water equivalent diameter is a diameter of a circle filled with water with the same cross-sectional area, and it has both geometric and X-ray attenuation information. And as you can see in this figure, the difference between effective diameter shown by yellow and water equivalent diameter shown by red are large in the thoracic region, as you can see, due to the presence of lungs with low X-ray attenuation. So third approach is using water equivalent diameter, DW. And obtaining of water equivalent diameter is not so difficult. The equations looks a little bit complicated, but it is not so difficult. Only information of pixel area and AW water equivalent area are needed to obtain the DW. To obtain the DW, and DW can be calculated by this equation. So AW is calculated by using this, and DW is calculated by using this. This is the same equation when we use to obtain the effective diameter. And then the SSD conversion factor is obtained from the table or regression equation provided in the APM report. In this case, the same conversion table can be used between effective diameter and water equivalent diameter. So in order to verify the accuracy of 3 types of SSDE, AP plus RAT SSDE, effective diameter SSDE, and water equivalent diameter SSDE, we compared between 3 types of SSDE and observed doses measured by small glass dosimeters. And in this experiment, 48 glass dosimeters were inserted into a female round phantom. This is a localizer radiographs of female round phantom. And the glass dosimeters were inserted into tracheal bifurcation level, breast level, and heart level, and also in the breast. Then the phantom was scanned with 16 slice CT scanner. It is in my university, in my faculty, with 80 kilovolt and 130 kilovolt respectively. These are the acquisition parameters. And after the acquisition, the glass dosimeters were read out and absorbed dose were calculated. Before experiment, the glass dosimeters were calibrated by using the same tube voltage to adjust the sensitivity of the glass dosimeters in order to reduce the effect of energy dependence. And these are the results. And according to them, the DW SSDE seems to be the best for obtaining SSDE conversion factor, maybe as you expected, because those values were similar between DW and absorbed doses. And absorbed doses were almost equivalent to DW SSDE at 80 kilovolt, but they are a little bit higher than DW SSDE at 130 kilovolt. So the tendency is estimated to be different according to the tube voltage and also the locations of dosimeters. And in 2019, the IEC has provided the document that provided standardized methods and recruitment requirements for calculating, displaying, and recording of SSDE, SSDE-Z, DW, and DWZ. It is called IEC 62985. So I will show you a little bit, explain a little bit about the contents of this document. And this is a new definition, SSDE-Z. And SSDE-Z is site-specific dose estimate at longitudinal position, at a certain longitudinal position, Z. And it can be calculated by SSDE conversion factor at longitudinal position Z by CTDI ball at longitudinal position Z. So this is the equation for obtaining SSDE-Z. And in other words, SSDE, total SSDE can be calculated by averaging SSDE-Z of all positions, as you can see in this equation. And this document has also introduced 2 new definitions. First one is DW reference Z. and the other one is dw imp z. And dw ref z is defined as dw, this one, calculated using the method calculated by this formula, as you can see, from all reconstructed images. So it is very time consuming. And dw imp z, this one is also a new concept. And it is dwz calculated using the method implemented by the manufacturer. So each manufacturer can decide how this dw imp z is calculated. So it is important to verify the accuracy of dw imp z. And it is dw imp z is defined because calculating dwz directly is difficult and time consuming. And delta relative z, this one, is defined as this equation. And the median delta relative z calculated for each anatomical region size has to be 0.1 or less, according to this document. Okay, so let's move on to the next topic, recent advances in CT dosimetry. So far, I explained about CTDI, DLP, and also SSDE, including the new definition proposed in the IEC document. So from now, I will show you some examples of recent advances in CT dosimetry. And this one is a conventional CTDI measurement, as I explained in the first part of this presentation. And the CTDI measurement is accurate for narrow single detectors, where the entire dose profile with scatter tails is within the correction region of the pencil chamber. That means that 100 millimeter length. But with the increased rows of detector elements, the z-axis coverage of CT scanners also increases more than the correction region of the pencil chamber. That means the beam width is more than 100 millimeter. Such situation happens in many scanners. And as those profiles get wider due to increased z-axis coverage, CTDI measurements using a 10 centimeter length pencil chamber and 15 centimeter length PBMM phantom, the conventional method, would significantly underestimate actual radiation dose. This is a problem. So for solving the problem for those measurement in wide beam CT, those measurement, IEC has proposed adjusted definition of CTDI, which is based on the measurement of CTDI1 by 10 centimeter length ion chamber and 15 centimeter length PMMM phantom, and measurements of CTDI air. And this method is called scaling method. This is the IEC method. And this method is easy to implement by measuring 3 types of CTDI, this one, and this one, and then obtaining the CTDI which is needed for the required beam width by using this equation. But this method is easy to implement, but it is also known to still underestimate actual CTDI at larger beam widths. And another method is called peak dose measurement method. Peak dose measurement method. It is proposed by APM. And in this method, a pharma chamber is used to measure the peak dose in a 60 centimeter length phantom at different beam widths. And the equilibrium dose, AEQ, as you can see here, is obtained by extrapolation of a mathematical formula. This is an extrapolation method. And a longer phantom is used in this example, a 60 centimeter length of a very long phantom is used to achieve equilibrium dose. So that a pharma chamber is adequate to capture peak exposure from the dose profile. However, the effect of phantom length on equilibrium dose has not been clarified. The 60 centimeter phantom is very heavy. It is not convenient to use. So if possible, the shorter phantom I want to use the shorter phantom. So the problem is how long the phantom is needed for achieving this purpose. So we will introduce you the study of verifying the effect of phantom length on peak dose measurement. And in this study, 256 slice CT scanner, Revolution CT, was used. And 6 types of beam widths from 40 millimeter to 160 millimeter were used. And the peak doses at the center and periphery were measured as air karma by a 0.6 cc symbol chamber by inserting this at the center of the phantom, which has active length of about 2 centimeters. And the chamber was inserted into the center of the phantom, and the peak doses were measured with single axial scan at center and 4 peripheral locations as like CTDI measurement. And 5 phantoms with different lengths were used, 32 centimeter diameter PMMA phantoms with 15 and 30 centimeter in length, and 30 centimeter diameter high density polyethylene HDPE phantoms with 20, 40, and 60 centimeter in length. So 5 different lengths were compared in this experiment. But PMMA and HDPE phantoms have different diameter, material, and density. In order to correct the influence of different diameter, material, and density on peak doses, the measured peak doses with 40 millimeter beam widths by both PMMA and HDPE phantoms were used to calculate correction factor. This is a correction factor. By calculating correction factor for HDPE phantom at center and for peripheral locations. And for calculating correction factor, 30 centimeter length PMMA and 40 centimeter length HDPE phantom were used to make the phantom length sufficiently long with respect to the beam width and to fully include the influence of scattered radiation. Okay. And nonlinear fittings were used to extrapolate the data to obtain the equilibrium doses, AEQ, at the center, like this, and periphery, which was the average over 4 peripheral regions like this, and that weighted for central and peripheral doses, 1/3 for center and 2/3 for periphery. This is the equation, same equation with the calculation of CTDIW. And this weighted AEQ was obtained also by extrapolation. And as nonlinear fitting, this equation was used. And the measured peak doses from 40 to 160 millimeter beam widths were fitted to this equation. These are the results of those measurements. And extrapolation was performed by using the solver function of Excel. Then the equilibrium doses, AEQ, were obtained by extrapolating until the infinite beam widths. So let me show you the results. At first, this slide shows equilibrium doses at center, AEQC. And the points on the graph shows the measured peak doses, and the curves show the fitted functions. And there was a tendency that central equilibrium doses decreased as the phantom length shortened, And the central equilibrium doses at 15 centimeter phantom length was 22.8% smaller than that at 60 centimeter phantom length. So in this case, when using only 15 centimeter length phantom, the dose was about 22.8% underestimate the real equilibrium dose. Second, this slide shows equilibrium doses at periphery, AEQP. And the points on the graph shows the measured peak doses, and the curves show the fitted functions like the previous slide. And there was a tendency that peripheral equilibrium doses did not decrease so much as the phantom length shortened. And the peripheral equilibrium dose at 15 centimeter phantom length was 6.47% smaller than that at 60 centimeter phantom length. Third, this slide shows equilibrium doses weighted for central and peripheral doses, AEQ. And there was a tendency that weighted equilibrium doses decreased as the phantom length shortened. And the weighted equilibrium dose at 15 centimeter phantom length was 10.1% smaller than that at 60 centimeter phantom length. So the weighted, and as you can see, the weighted equilibrium dose was saturated when the phantom length was 40 centimeter or more. At 40 centimeter phantom, the AEQ was 18.2 milligray, but at 60 centimeter, it was 18.0 milligray, so almost saturated at 40 centimeter. So this is a discussion of these results. And if comparing delta AEQC and delta AEQP, it was found that the influence of the phantom length was larger at the center than at the periphery. So I thought this was because the ratio of scattered radiation components generated in the phantom was different between center and periphery. The ratio of scattered radiation components generated in the phantom was large at the center, but the ratio of the scattered radiation components generated in the phantom was small at the periphery. And with regard to delta AEQ, AEQ at 15 centimeter phantom length was 10.1% smaller than that at 60 centimeter phantom length, as I explained earlier. And the influence of the phantom length was large. This was because the shorter the phantom length, the less scattered radiation in the phantom. But the AEQ was saturated when the phantom length was 40 centimeter or more. From this result, I think the peak dose measurement was better performed using a phantom length of 40 centimeter or more when the accuracy of AEQ is important. Okay, so I will move on to the next topic. And this is an example of dose calculation software, a CT dose calculation software named WAZA-ARI version 2. And this has been developed in Japan, and this can be used in free of charge, only registration is needed. And in this software, after inputting the parameters here, and then after clicking the calculation, not only the organ doses, but also effective dose can be obtained for each scan. And it has several types of voxel phantoms, including adult males and females, and with different physique, and boys and girls with different ages, like this. And when inputting a certain height and weight, I cannot find, but in the new version, when inputting a certain height and weight, it can calculate with an optional phantom according to its height and weight. And I think this software is highly versatile, and it can be used to easily obtain patient dose estimates. But another method is the Monte Carlo simulation method. And it is superior in that it can be calculated by freely combining source and object models. So it can provide more detailed dose information not available with those calculation software like WAZA-ARI version 2. But the calculation accuracy needs to be verified by comparing with the results of direct measurement method. And there are several types of Monte Carlo simulation codes, such as FITS, EGS4, EGS5, and Giant4 are many types of Monte Carlo simulation code. And such code can perform calculation according to the input file like this, and tally results can be obtained after calculation. This is the screen of during calculation. So now my research group is trying to develop Monte Carlo simulation program for dual energy CT. And this explains how the fast KV switching dual energy CT is simulated. Fast KV switching technology is introduced by GE Healthcare. Also, Canon is also applies this method. And those calculation results of 80 and 140 kilovolt are obtained every 15-degree interval like this, and they are combined with a ratio of 2:1 to obtain those results of 80 and 140 kilovolt. And these are those calculation results of thoracic single and fast KV switching dual energy CT of the real patient. This is a movie. And you can, left one is single energy CT, right one is dual energy CT. And you can see that the dose distribution of both are slightly different depending on the location. It may be a little bit difficult to identify the difference, but there are some difference between single energy CT and dual energy CT, even though the CT level was equivalent. And this explains how the dual source dual energy CT is simulated. Those calculation results of 80 or 100 kilovolt at low energy side and 150 kV with thin filter as high energy side are obtained with every 15-degree interval like this. The start angle is different, about 95% of difference from tube A and tube B. And they are combined with the ratio of 2:1 to obtain the dual source dual energy CT, those results. And these are those calculation results of dual source dual energy CT. And absorbed doses for 80 and SN 150 kilovolt were slightly higher than those for 120 kilovolt and 150 kilovolt with thin filter at the anterior surface region, as you can see, under the same CT level. However, these differences are slightly lower than for 120 and 150 kilovolt with thin filter at the lateral surface side, as you can see here. The difference was very slight, but after calculation of these doses by using the Monte Carlo simulation, and results were combined for both low tube voltage side and high tube voltage side, we can observe the difference of those results between single energy CT and dual energy CT. And I already showed some examples of Monte Carlo simulation results of CT dose calculation, but the problem with the Monte Carlo simulation method is that the calculation time is very long to ensure high calculation accuracy. For example, I showed the results of fast KV switching dual energy CT dose distribution map, but we needed for about a few days to obtain the results. Very long time is required. So we are trying to speed up the Monte Carlo calculation by parallel computing and output and read of voxel data in binary format. But it is still difficult to significantly reduce the calculation time. So to solve the problem, attempts have been made to estimate those maps from CT images using the trained deep neural network DNN model. And in these papers, these are the papers that tried to shorten the time of calculation by using the DNN model. And in these papers, the collected CT images and the Monte Carlo produced those maps were processed and used for the training of the DNN model. And those maps were produced from CT images using the trained DNN model. And this figure shows workflow and architecture of the DNN model. And those prediction model consists of one input layer and 3 hidden layer, 1, 2, and 3, and one output layer as shown in this figure. And CT image and mask image are combined like this to create a masked CT image, and X-ray tube current, the coordinate, water equivalent diameter, and organs Hansfield unit numbers are used as their input information. And this table shows the evaluation result of those prediction DNN model. And the developed machine learning based method resulted in a 99% reduction of the processing time. This is very surprising. The result was very, very similar between DNN model and Monte Carlo simulation, as you can see. So I believe there's a potential for such method to shorten those calculation time dramatically. Okay, so this is the final slide. I will sum up the topics of this presentation. I explained about CTDI, DLP, and SSDE, including new definitions shown in the IEC document. Then I showed you some examples of recent advances in CT dosimetry, including peak dose measurement for wide beam CT and Monte Carlo simulation. Okay, so that's all for my presentation. Thank you very much for your kind attention.
Thank you very much, Professor Kosuke Matsubara, for your nice presentation and very informative regarding the basic and recent advance for the CT dosimetry. I think we learned a lot from you. And we also got one question for you. I think, so maybe you can answer. So the question, it's just a quick question, okay? Can we use our existing pencil ion chamber for this new CTDI measurement?
Oh, thank you very much for your question. Sure, you can use the conventional existing pencil ion chamber. In this method, it means the IEC method. We use conventional phantom and also conventional CTDI chamber. So it is a very convenient method, but it is already known that it also underestimates the real CTDI. So I introduced a new method of peak dose measurement. But in this method, peak dose measurement method, the pharma chamber is required. It is a shorter one, very shorter one. The active length is about 2 centimeters. So for applying this method, you have to prepare a new chamber, pharma chamber. Thank you very much.
Okay, thank you very much for your answer. Okay, and then I think you will have a chance to answer the question again for the Q&A session after the next presentation. Okay, thank you, Professor.
Thank you very much.
Okay, so let's move to the next speaker. For the next speaker will be Professor Dr. Atsushi Teramoto. So before we start his presentation, so let me introduce about the background of Professor Teramoto. Professor Dr. Atsushi Teramoto, he got a bachelor degree in engineering from Department of Electrical and Electronics Engineering from Meiji University, and also he got a master's degree and PhD degree in engineering from Meiji University and Gifu University in Japan. So he served as the committee for the various activities such as the counselor of the medical imaging and information science, the committee member of the image science division of the JSRT, the editor-in-chief of the medical imaging and information science, and the associate editor of the IEEE Journal of Translational Engineering in Health and in Medicine. He also got several awards for the honor and the awards, such as for the award for the outstanding for the young researcher, and also the award for the outstanding young researcher from the JSRT in 2012, the award for the outstanding young engineer from the JSRT in 2014, and the best paper award from the IFMIA in 2015. His research interests focus on the computer-aided diagnosis in PET, CT, MRI, mammography, pathology, and endoscopy. In general, medical imaging, such as for the noise reduction automated measurement, and also for the computed tomography for the image reconstruction hardware development. Okay, please welcome Professor Dr. Atsushi Teramoto.
Okay, thank you for your excellent introduction, and hello everyone. Can you see the screen?
Yes, we see your screen.
Okay, okay, and I am at Teramoto at a major university. It is a great pleasure to be able to get an opportunity to speak here. In this presentation, I'd like to talk about the fundamentals of deep learning and its application in medical imaging. I worked in the company for 10 years. Then I worked with Dr. Tsujioka, the first speaker at Fujita Health University. After that, I took a position at the Faculty of Information Engineering, major university. Currently, I teach about data science, AI, and computer programming, and so on. In my laboratory, there are more than 20 students from major university and Fujita Health University. They are studying every day to develop new AI technologies for medicine. Today, I focus on the basics for the AI technology and introduce some application for CT imaging. First of all, let's talk about AI history. There have been three big moments called AI booms. During the first two booms, the people got really excited about AI, but then they understood its limitation, and the excitement faded away. So now we are in the third boom. The AI is meeting a lot of expectations and sparking lots of new technologies and products. And in 2022, around here, we saw a bunch of new applications using large language models, LLM, like ChatGPT, bringing AI even closer to humans. So some folks think this might lead to a fourth boom. In terms of image recognition processing, the conventional understanding of image was carried out by procedure like this. The first, the feature related to the shape, color, and size and texture are extracted from given images. After that, the category was determined based on those features using machine learning methods. As you know, the radiomics is based on this approach. However, there are some challenges that are difficult to solve with conventional technology. Here is an example. These images are from the context of similarity between pets and their owners. Owner and pet are very similar. I think it may be impossible for a conventional method to accurately distinguish between the human and the dog from such an image with similar features. On the other hand, deep learning method includes feature extraction and classification. The characteristic feature of images are calculated automatically, and it can classify the object. That is, the deep learning can acquire the classification ability by simply only giving the image without taking difficult procedure such as feature extraction in the conventional technology. So, what kind of AI could be used in the hospital? The AI will automatically detect disease and prevent doctor from missing of disease. Also, the robots will be equipped with AI. They will be more human-like. For example, the AI-equipped wheelchairs are beginning to be used in some hospital to take patients to their destinations. In addition, the robots may be available to do jobs like a radiological technologist. It will be possible to take pictures with the patient without worrying about the radiation exposure. Okay, let's begin with AI basics. First of all, I'm showing the relationship among the technical terms about artificial intelligence. The first, artificial intelligence, AI, is a generic term for technologies, the intelligence demonstrated by machines. And the machine learning is a subset of artificial intelligence, the techniques to give computer the ability to learn. And artificial neural network is also the subset of machine learning, the computing system inspired by neural network of animal brain. Finally, the deep learning is a deep and a complex structure of artificial neural network. In this lecture, first I'd like to talk about artificial neural network, and I will go deep learning. The artificial neural network, ANN, is a computer system inspired by neural network of animal brains. In other words, it simulates the biological neurons. As you all know, our brain consists of many biological neurons and have the structure shown here. There are soma, axon, and dendrite. When more than certain input, a certain stimulus is applied to the dendrite, and the pulse comes out, and it goes to the another neuron via the axon and synaptic connection. About tens of billion neurons are connected in our brain. The biological neurons has simple behavior, so we can make the biological neuron in the computer. It is represented as shown on the right. We call it artificial neuron. In this figure, the small x is an input value, and W is a weight representing the strength of synaptic connection to each input. And Y is the output of artificial neuron. It can be calculated by the following equations. They are very simple. In brief, the output of the artificial neuron is determined based on the total of weighted input signal. An artificial neural network is a combination of many artificial neurons. There are various structures of networks, and currently the layered feed-forward layered neural network shown here is widely used. In this figure, the round symbol, circle, this circle stands for the artificial neurons. And three-layer structure is usually used, and it is called input layer, hidden layer, and output layer. And neurons are connected with different weighting among the respective layers. The data are given to the input layer, and they go to the hidden layer and output layer in turn. And finally, the processing result is obtained from output. In the conventional technology, the three layers of artificial neural network were often used, but their processing performance has limitations. So if we want to obtain more processing ability, then we have to increase the number of layers, not three layers. So we have created an artificial neural network with deep structure by increasing the number of hidden layers. This is the technology behind deep learning. The various deep learning methods have been proposed, and one commonly used in the image processing is a convolutional neural network, CNN. We call it CNN. A CNN is architecture inspired by the visual cortex of animals. When we perceive an object like this, the light stimulation is initially received by the retina of our eyes, and this information were then transmitted to the thalamus of the brain around here. In the primary visual cortex located at the back of brain, the basic features such as line and edges I draw as a red line, and these features are extracted separately. And these features are then integrated across subsequent layers from second to eighth visual cortex. And finally, the object is recognized based on our previously acquired knowledges. The experiments using cats were conducted to reveal the mechanism of vision I talked before slide. The photo captures a cat during one of these experiments. It somehow looks melancholic, that's it. The electrode were inserted into the cat's brain, as shown in this figure, and to observe its responses to various patterns. As a result, researchers found that when recognizing objects, the brain captures their contours and integrates them to perceive objects. This slide shows the typical CNN architecture for image recognition based on the knowledge of the experiment using cats. The CNN consists of multiple convolution, pooling, and free connected layers. When performing the image classification, the which is a popular application of CNN, the images are directly given to the input layer, and the classification results are obtained from the output layer. Now, let's take a look at the convolution, pooling, and free connected layers. In the convolution layer, feature of images are extracted by convolution. Do you know what convolution is? The convolution is one kind of mathematical operation on two functions to produce the third function. In the image processing field, we use convolution for the spatial filtering, such as smoothing and edge enhancement. In the convolution layer, features of images are extracted by filtering. By filtering, we can obtain simple features such as edge and brightness of the image, like a first visual cortex of the brain. In this layer, a lot of images, about several hundred of images, are obtained from the given image. We call them feature maps. And in the pooling layer, after the convolution layer, the feature maps subsampled. In other words, the original images shrinked to the small image. In this figure, we can see the L-shaped pattern in the 4 by 4 pixels. When a computer processes these images, images are translated to one-dimensional, like this. We can recognize two patterns easily, but it is a little difficult to understand for computers. The pooling layer shrinks the image. In this example, it is shrink to the 2 by 2 pixel patterns as shown on the right. The result will be the same pattern no matter which of top and bottom images are given. Therefore, we can reduce the influence by object position in the recognition. This slide shows the feature map images of each layer in CNN. The cat image is given to CNN. The many features are extracted like this. As a layer gets deeper, the many small images are generated as the feature maps. We can get many feature values from one image. In the fully connected layer, the final classification is performed using feature maps collected by convolution and pooling layers. We usually introducing an artificial neural network for this part. In the final output layer, the output units equal in number to categories are prepared. And the unit with maximum output value becomes a classification result. In this example, the unit corresponding to the cat is having the maximum output of 0.8. So the classification result is cat. Also, we can use the output value as a probability of something. So this means that we can use the CNN as a regression problem. The deep learning cannot do anything before training. For the training of network, huge number of input image and corresponding ideal outputs are prepared. And error between the output and the ideal output is calculated. The parameters in the network are adjusted to reduce the error. As shown in the figure, on the right, if the network and data are good, and the error will go down like this. Okay, next I will introduce the recent technology named attention mechanism. The attention mechanism can express where to pay attention to given data. This idea is very, very powerful, and many methods using attention mechanism have been developed. For example, suppose we want to analyze the kidneys from CT image, and the image contains not only kidneys, target kidneys, but also other organs like this. Since it is more likely to be able to analyze the kidneys more accurately if we focus on the kidneys, we prepare the kidney mask like this. We prepare the kidney mask to pay attention on kidneys. By using this masking process, the kidneys are extracted like this, that we can analyze focusing on kidneys. While CNN extracts local relationship as the features, on the other hand, the attention mechanism can focus on the data that exists at a distance at the same time. Probably, if you want to recognize two kidneys on the left and right side at the same time, you will get better accuracy than with CNN. The attention mechanism show excellent performance for natural language processing, text processing. Since the natural language we use in our conversations and writing often involves relationship between the words located at the distance from each other. One of the application of attention mechanism, the transformer model has shown superior performance in natural language processing and has been used for the machine translation and text generation in ChatGPT. The transformer can be applied to image processing as well as natural language processing. The vision transformer is the most well-known model, and its conceptual diagram animation is shown here. In this model, the image is split into smaller patches, smaller parts. Each of them converted into the vector. These vectors correspond to words for natural language processing. Then the features can be extracted from the vectors given by transformer, and image classification can be performed by fully connected layer. Its performance is better than that of conventional CNN. Okay, this slide summarizes the typical processing that can be conducted with deep learning and its medical applications. One is the classification. The classification is a process of inputting an image and dividing it into multiple categories, multiple class. For example, it can be used to determine the benign or malignant or cancer type of lesions. And regression and prediction are process of calculating continuous value related to images or numerical data. The examples of application include survival prediction and response prediction, and those estimation that Dr. Matsubara talked before presentation. And the detection and region extraction is a process of inputting the image and finding the specific object or extract the target region from the image. And it can detect regions, the disease, and the organs in the image and determine their extent. The final application is generation and translation. Okay, and we can automatically generate non-existent image or convert an image into another image. There are a lot of researches being done for medical applications, and there are examples of research on should disease generation and modality translation and report generation. Okay, I'd like to explain about AI application developed by our laboratory. First, I will introduce AI-based X-ray imaging technique for chest X-ray. In the chest X-ray image, the bone components such as ribs account for 75% of images. If lung disease is overlapped with bone, it becomes difficult to detect. So therefore, we conducted a study on the bone suppression processing in chest X-ray images using conventional neural network. In this study, chest X-ray images were split into patch images, and they were given to the CNN. The CNN recognized the bone component and predict the density of bone. When this process is performed on entire image, a bone image is obtained like this. And finally, by subtracting the bone image from the original image, the bone suppressed image is obtained. Using this technique, most of bone components disappeared in the images. This example shows a pattern of nodules raised by bone suppression. There are two nodules. They are overlapping the ribs, but are now clearly visible after processing. The deep learning has also been used for lung region, lung nodule detection. And this slide is an example of my first study using deep learning for lung nodule detection. In this study, the CT and PET images were image processed and enhanced nodule patterns and detect them as candidate regions. We used the conventional image processing technique to detect the lung nodule. Since there were many false positives among them, so they were reduced to using CNN and traditional machine learning method. And this slide shows the result detected by this method. The red circle shows the nodules. They could not be detected by the conventional method. The detection sensitivity of this method was 90% with the number of false positives per case of 4. As a result, a sufficient acceptable detection performance was achieved by introducing CNN. And this slide shows a study on the detection and classification of interstitial pneumonia. There are many different types of interstitial pneumonia, and including incurable disease such as IPF. In this study, we extracted and classification of the interstitial pneumonia. In this method, 3D CT images, multiple CT slice images were given to the 3D unit. Unit is a segmentation model using CNN. and it trained to output IPF and non-IPF distributions. And this slide shows the extracted results, and the green region were detected as a pneumonia. The result of matching of physician's sketch with the extraction results were acceptable, and showing the 77% agreement. And in the remaining time, I'd like to introduce image generation and translation techniques. They are the cutting-edge technology of deep learning. And the generative AI models can be used to generate image from random sequence, random value. We can get the should realistic image from the random value. And there are also models that convert one type of image to another. And furthermore, there are models that generate image based on the given text, like a stable diffusion. There are many models for image generation from now on. Among them, the Generative Adversarial Network, GAN, is very popular. The GAN have two networks, a generator network and a discriminator network. The CNN in this network, the CNN architecture is usually used. In the two models, the generator network generates the data that is as similar to real data as possible. And the discriminator network distinguishes between the real data and fake data. The adversarial training between the two networks can generate the realistic data from the generator. This slide shows the generated images at the initial and intermediate and end of training phase of GANs. And this is an example of the generation of the number from the 0 to 9. The GAN was made to generate image of a number of numbers 0 through 9 like this. In the early stage of training, the only broken number patterns were generated, but in the end stages, the high quality handwritten number were generated like this. In our laboratory, we have applied this technique to classification of lung nodule in CT images. Often, there are few images or unbalanced data to diagnose lung cancer. To compensate for the lack of images, we generated lung nodule patterns with GAN and applied them to train the AI. The image on the left is a result of generating a CT image of lung nodules, and the generated output is these images, and for the benign images, benign nodules, the smooth and smooth contoured nodule were generated, while for the malignant nodule, spiky speculars were drawn. The next, we provide the generated and realistic data to the CNN and classified them as benign or malignant. The result showed that generated images enhanced the classification performance. And we can also convert images to each other using AI. The cycle GAN is a mutual image transformation architecture that combines two GANs to transform one type of image into another. This video is a result of converting a horse video into the zebra video. The AI directly produces highly accurate images without introducing complex image processing technique such as object recognition or the painting technique. The image translation technology has already been used in many studies. In our laboratory, we have attempted to convert non-contrast enhanced image to contrast enhanced image to assist CT examination. The non-contrast images on the left was translated by the cyclogram, resulting in an image with contrasted carotid arteries, as shown in the right. By using this technique, the enhanced area can be predicted and appropriate timing of imaging can be determined by the monitoring the area. On the right side is an example of CD coronography with barium residuals eliminated by cyclogams. The white barium area have been removed in the processed image, making the inner wall of colon easier to observe. And here is also our work. The CT images were generated from the doctor's sketch of the lung. The top images are the real CT image, real nodule patterns. This real CT image are sketched by several physicians, becoming input information like this. These are the doctor's sketch of the nodules. And CT images are generated from these sketches like this. Although the sketches differ from the doctor to doctor like this, the CT image patterns of nodule are generated accordingly. Also, the conversion from the sketch to CT image can be performed in the real time. Here is a demo video of the application that incorporates the conversion models. The image generated in this way can be used for training of AI or to classify nodule or for educational purposes. The last application is not for CT images. The study about the generation of diagnostic reports from chest X-ray and pathological images. The LLM language model, large language model is combined with image processing AI to output image findings. Under the limited conditions, the acceptable quality text were obtained like this. Okay, this is the conclusion. In this presentation, I explained the fundamentals of AI and its application to medical imaging. The modern AI is built on artificial neural networks, and it mimics the function of human brain or vision system. And AI is capable of image classification, region segmentation, image generation, and image transformation. They have been implemented in CT image processing with beneficial results. Okay, that's all for my talk. Thank you for your attention.
Thank you very much, Professor Teramoto, for your excellent presentation regarding the application of the deep learning in medical imaging. Yeah. So I think so. It's time for the Q&A for our immediate speaker for Professor Tsujioka, Professor Matsubara,
Yes.
and Teramoto. Yes. So for the audience who have any question, you can type your question in the Q&A box. So right now, I think we have one question from the audience to Professor Matsubara.
Okay.
Yeah. The question is, the currently available phantom are usually 15 centimeter in length. Is it suggested to develop longer phantom? And can we still use the current phantom and the current CTDI volume method in our facility while longer phantom are still unavailable? Thank you.
Okay, thank you very much for your question. And currently, IEC has used a method called a scaling method, as I explained, by combining CTDI 100 measurement of reference beam width, it is about 20 millimeter beam width, and CTDI air measurements of target and reference beam widths. And they can be measured by using conventional 15 centimeter length BMMA phantom and 10 centimeter pencil chamber. Conventional tools can be used. And in this method, measurements can also be made using incremental steps of the ion chamber if the beam width is more than 100 millimeter. And so answer of your question is yes, and you can use conventional phantom and ion chamber. And you don't need to prepare longer phantom and shorter chamber. And I think peak dose measurement that I explained in my presentation is still under the research level, not appropriate for using in daily QA and QC. Thank you very much.
All right. Thank you very much. So, and I hope that Professor Matsubara answered your question. All right. So, are there any questions from the audience? Okay. So, maybe, okay. I think we got one question maybe for Professor Teramoto regarding for the AI. So I just wonder what are the main contribution of the AI to medical physicists in medical imaging workflow? Please, Teramoto Sensei.
Okay. It's very good question, and I think the currently the disease detection, lesion detection using medical image is for the radiologist, doctor, but this technique can be applied to the radiological technologist and the medical physicist. The radiological technologists take pictures, radiological pictures of the patient, and if they use the AI software, the additional inspection can be conducted at the modality, in front of a modality, so the workflow will be changed.
Okay, all right. So thank you. So I hope that Professor Teramoto answer your question. Yes. So yeah, thank you for your nice presentation from the audience to Teramoto Sensei. Yes. So regarding from the previous question for Teramoto Sensei, I think right now there are many of the software installed in the hospital. I mean, for the analysis and also for the workflow to help medical physicists. Yeah. So what is the thing that we should be careful when use of this software that based on the AI? So for your recommendation, so what is the point that we should be careful when use this software that based on the AI? Yeah.
Yes, and so the AI becomes excellent. AI shows excellent performance recently, but not intelligent. Not intelligent, same as humans. So the usually mistakes. So we have to check. We have to check the result of AI, and recently the chat application like the Chat GPT, there is a hallucination of the output. So we have to think about the result more deeper than before.
Okay, all right. So thank you. So it means we have to verify that AI software before using, right? That is the beginning part. Okay, thank you. Are there any questions from the audience? For those who have questions, you can put your question in the chat box. Okay, I think again for the AI, how training the model is made independent of the input. Yeah, the question is how training the model is made independently of the input.
Yes, I don't understand clearly of this question, but maybe we need to train for independent images. For the CT images and the MRI images, we need the individual. We need to train the individual models. I'm sorry.
I'm not sure. So I think maybe it's like we have the training data set, we have the input data set, and like and I'm not sure about this is how to train the model independently. It's
Yeah.
not,
Yeah.
yeah. Okay. So.
And the question from the saying the question about the software of the AI.
Yeah. So yeah, another one is about how it is still for the AI. Yeah, and also for the CT as well. How AI contribution can relate to CT diagnostic dose exposure reduction, especially for pediatrics.
Pediatrics. Yeah. Yes.
It's quite tough question.
Currently the application of the AI reconstruction is restricted to the adult body. So the company needed to train using pediatric CT images to get a better result.
Okay. And another question for Teramoto Sensei as well. How reliable do you think AI decisions are? Yeah, how reliable do you think AI decisions are?
How reliable AI output? It's a difficult question. It depends on the application. So we need two criteria to evaluate the image quality and the detection result. this is our future work to establish the criteria of evaluation.
So maybe I have one question for Tsujioka Sensei. So regarding for the photon counting CT.
Yeah.
Yeah. So how about the direction of the photon counting CT right now? So in your opinion.
Now the photon counting CT is now developing, and detector is cadmium telluride, and the silicon is different, and maybe in near futures the performance is we can understand the performance and disadvantage and the advantage. So just I'm waiting and researching, but now is no answer. Maybe after next year, and but the big problem is computer speed. The data set is very about 10 times or 20 times bigger, and that's high speed. For the pile-up is a very important effect, but it needs a very short time detecting. Maybe near future we are waiting.
Okay. Yeah. And I think also for the price of the counting CT is still quite expensive compared to the to the current CT technology right now.
Yes.
So is it possible to reduce the price from the company?
Last ECR, European Congress Radiology, in the session, the one audience asked to presentators, why is photon counting CT is so expensive? So presenter answered, photon counting CT is now is a special CT for very high accuracy and very high resolution, special resolution CTs, not for screening CT, and it's just a special studies. But it's a latest change to usually use the CT now.
Yeah. Okay. Thank you so much for your answer. Yeah. For your point of view regarding the photon counting CT. So we got two questions maybe for Matsubara Sensei. Is there any difference method of the dosimetry for photon counting CT and MSCT?
Okay, thank you very much for your question. The answer is no. And in case of photon counting CT, we can use the conventional dose measurement method. And can I move on to the second one? So we use CTDIW to calculate cancer risk. CTDIW underestimates or overestimates. It depends on the patient size. But anyway, underestimates or overestimates the organ doses, and it is not appropriate to be used for estimating cancer risk. And SSDE may be helpful for estimating it, but further research is required, I suppose. Thank you.
Thank you. So I hope that Professor Matsubara answered your question. Yeah. All right. So I think that okay. One more question from the audience regarding the AI. Yeah. What kind of CT images are needed for better AI usage?
Thank you for your question. It's a difficult question for me. Mr. Tsujioka, how do you think?
Sorry, this is my question.
This is a question from Professor Tsujioka.
Sorry. Of course, the high quality CT image is ideal. But we have the technique to reduce the artifacts from the image using AI. So I think there is a little restriction about the CT images. CT
Yes.
image has a CT values, and so it's very easy to handle using AI.
Yeah.
Very good modality for AI.
So my idea is just diagnosis by the radiologist and AI is different. So image for the screening is if the image noise is very high and very low dose, but it's not so good for radiologists. However, the deep learning and AI machine is good for diagnosis. Only screening is good for patient dose reduce and diagnosis is enable. But it's not special high spatial resolution and high contrast resolution. But screening is I think it's a very low dose examination. It's a future separate technique.
Okay, I understand your question. And in future, the computer diagnose, AI diagnose the screening CT image. But currently, the radiologist have to verify the result. So we need to keep the image quality.
Yeah.
All right.
So can I comment about AI from my side? Okay.
Okay.
I want to comment about the AI, and I understand that many participants today have interest in AI, and I think medical physicists need to understand what the AI is and how it can be used in such as software in the software. Only using software is not enough because it is not accurate. Accuracy is not verified. How the accuracy is, and it is not clear. So medical physicists need to have enough knowledge of AI, and if possible, they should have knowledge and skill of such as writing code or developing something using AI. Thank you.
Yes, I think so. And currently, there are many information about programming, and also the AI assists the programming. So we can easily to make the code for the AI programming.
That is a good comment from Matsubara Sensei. Yes, regarding for the AI. Yes. Teramoto Sensei, do you have a chance to do a research the AI regarding in nuclear medicine imaging? Have you ever like used the AI in nuclear medicine imaging, like in PET?
Yes,
Yeah.
yes. I'm studying about PET CT and dedicated to breast PET images.
So can you specific for the example of the AI used in the PET CT?
Specified.
Like to detect the cancer from the PET CT or?
Yeah, lung cancer and breast cancer.
Ah.
Yeah.
So in this case, so how many patients need to develop the AI in this case?
Yes, currently the deep learning need the big data. So I collaborate with the university hospital and clinic, and more than 80,000 scans, 80,000 scans of PET CT image. We need a big data.
Wow, that's a lot. All right. I think yeah, maybe so. I'm not sure this is the last question or not. To all speakers, yeah. Do you think that to do reporting of the images for diagnostic radiology, we can only use medical grade only, or we can use any common monitor which have equivalent standard. Equivalent standard specification with medical grade monitor. I think this question may be about the monitor.
I think this question is needs for the display device.
Yeah,
Yes.
yeah, right.
Yes,
so I think it's about the can we use the only medical grade or can use any common monitor that the standard or use the medical grade.
In Japan, the special medical monitor, dedicated medical monitor is needed for the diagnosis.
Happy journey. Have a nice day.
I think that is the standard for the display device in medical imaging.
In the latest CT machine is changed to a high resolution machine, and now is a conventional matrix size is 512 by 512. Now is changing to 1024, 1024, and then small and 2048 and 2048. In diagnosis is needed the medical grade.
And also for the photon counting CT again. So do we need a specific display device?
Of course.
Okay. Thank you so much. I think that's all of the question from the audience to our invited speaker. So yeah, on behalf of the, I think today we have a very good presentation from our speaker. So, and we have a very good discussion, from our speaker as well. So, on behalf of the AFOMP, I would like to appreciate and thank you all for the invited speaker, Professor Kosuke Matsubara, Professor Katsumi Tsujioka, and Professor Atsushi Teramoto for providing the very informative and very fascinating lecture to our audience. So thank you so much. And I would like to thank all of the participants to join the AFOMP webinar series today. So, and hope that you will enjoy the presentation from all our invited speaker, and hope that we hope to see you again for the next episode of the AFOMP webinar series. Thank you so much. See you.
Thank you very much.
Yes, Kitiwat, I think there is one last question.
Oh, yeah. Okay. All right. Just one last question. Which software used for medical imaging segmentation-based result?
Okay, I send a message. And the unit architecture is most common architecture for the segmentation. Please try it first.
I agree with you.
Okay. Okay,
Thank you.
I agree with you, but yeah.
Yes, I think that concludes our session today. Thank you very much, all of you. Thank you very much, Professor Tsujioka, Matsubara, and Teramoto for very enlightening and motivating talks on basic and latest technology CT. And it's very motivating for many of the youngsters to explore more into the applications, dosimetry, and AI use in the image analysis. Thank you very much, Kitiwat, for moderating this session. And on behalf of AFOMP, I thank all the participants, all the speakers, and the moderator for spending your time. And welcome you all for the next AFOMP monthly webinar next month, first Thursday. Thank you very much.
Thank you.
Thank you very much.
Thank you very much.
Thank you very much.
Okay, bye-bye. See you.